I invite Professor Sheldon Stone from Syracuse University to give his talk on indirect manifestations of new physics, experimental tests.
We'll commit murder, but I think we can avoid that here. If I don't get interrupted during this talk, I will consider that I haven't done a good job. So please help me, and I hope to make provocative and even correct statements. So I'll be talking about indirect manifestations of new physics through experimental tests. Okay. And, well, you've heard much about the reasons for why we expect that there'll be new physics beyond the standard model. I just want to remind you that the standard prescriptions generally involve things that may only be related to gravity. Dark energy, dark matter, gravitational lensing, hierarchy problem. Even the hierarchy problem, people keep talking about the Planck scale, even real high energy theorists. And the Planck scale is a gravitational scale. Just a comment. Okay, now there are reasons that I like to relate to, even though they're only related to 4% of the energy in the world, namely that of the quarks and the leptons, mainly because I live in that world. Okay, so to me, these are very important questions. The first problem is, why are there 3 replications of quarks and leptons? Second one is baryogenesis. The amount of CP violation observed so far is small, but only by about 9 orders of magnitude. So we would really like to understand how the world came into existence and why we're here. Okay. And this also implies that new physics must exist that we haven't uncovered to generate the needed CP violation. And we would like to explain the CKM couplings. This has been referred to many times by Andrea and Marina, and it's a very important question, as well as not only the CKM elements, but the masses, etc. So are these masses related to the CKM elements? Or is there some way of relating them beyond simple numerology, which has been tried in the past? So what I'm going to be talking to you about is really in the context of heavy flavor physics, so I should define it. So flavor physics is the study of interactions that differ among flavors. Heavy means not standard model neutrinos or U and D quarks, maybe S quarks, and we concentrate here on B quarks with a little bit about C quarks. Now, T quarks are too heavy. You can see this here. They're just too heavy. They don't form mesons, so they really don't do too much that's interesting for us. Okay. CB quarks and taus, and maybe heavier neutrinos, they're just right. And what it says here is, don't step on it, it makes you cry. And the S and U quarks, in some cases they may be heavy enough, but generally they're too light. And the U quarks, the D quarks, and the standard neutrinos are far too light for us to study in these contexts. Now, far be it from me to tell what theorists do, but I've been told that a theorist's task is that, given a theoretical model, all the data has to get explained. So the model must thread through all experimental constraints, denoted here by 12 axe handles here, and the theorist has to fire an arrow and get through each constraint. So one measurement in principle can defeat the theorist, but we actually seek a consistent pattern of measurements. Generally, if somebody comes out with one measurement and say it violates the standard model, you tend to be skeptical. So you really want to get a pattern here. But the theory really does have to fit all the real or correct measurements. Now, flavor physics, as we started, it was a lot of fun. We were like children in the candy store playing around with things and learning all kinds of stuff, and it was fun. But actually now, it's become a very potent discovery tool. So while measurements of these CKM parameters and masses are fun, the main purpose of flavor physics is to find and define the properties of physics beyond the standard model. Just like you heard in the other talk before, looking for things directly is one way of doing it, but I want to show you that looking for things indirectly is another way. So flavor physics probes large mass scale versus virtual quantum loops. An example of the importance of such loops are changes in the W mass. Now, this was known before the Higgs was discovered, and even before the top was discovered, that the changes in the W mass were proportional to the W mass divided, the top mass divided by the mass of the W. So you could learn things about the top by looking at the W mass, and once the top mass was pinned down, you could look further and you can get information on the Higgs mass because the W mass depends a little bit on the Higgs mass through these virtual diagrams here. Now, another way of saying this is to just bring you back to some more elementary physics and the importance of these loop diagrams is the Lamb shift in atomic hydrogen. There's a small difference in the energy levels between the 2s1/2 and 2p1/2. These levels should be of equal energy in lowest order, but when you put higher order quantum loops in from QED, you get an energy shift, and the energy shift was exactly what was calculated by these loops. So this was a very early example of the importance of quantum loops and looking at new physics. And new physics in this case was confirming QED. Now let me give you one example of strong constraints on new physics. There's a process in B decays where the B quark emits an S quark and a photon. And then, of course, there's a spectator antiquark here, but we're not concerned about that. We're doing inclusive decays. We don't care how this S quark ends up in the final state. We only care about the photon. And this diagram, this can be described in the standard model by this diagram involving a top quark. And it's a very similar diagram here, okay, and W's. And then the photon comes out, and the photon could also come off the W leg, rather, as it's shown here. Or it could even come from the initial B quark. And there are various effects. Now, this has been measured fairly accurately to be something like 3.4 10 to the minus fourth with an error of about 8%. Now, the theory is also fairly accurate, about the same accuracy, in fact. Okay. And there's been a lot of work on this over the years. And this ratio is very consistent with the standard model. It's about within 10%. Now, this actually limits most new physics models. If you generate too big a beta S gamma or too small a beta S gamma rate in your theory, you won't agree. For example, now you can take any specific model. You can take a 2 Higgs doublet model. So here you replace the charged W's with charged Higgses, okay? And you put these diagrams in, and they interfere with the standard model diagrams. And if you do this in this particular model, the results can be plotted here. Okay, the experiment is between these red bands here. The standard model, which is consistent with it, is between these blue lines. And in this theory, you get this band, and this represents the theoretical uncertainty. And if you look here where the lower theoretical uncertainty band touches the upper experimental uncertainty band, and you look down here, and this says mass of the charged Higgs, that's at 385 GeV. So this one process says that in this particular model, the mass of the charged Higgs has to be larger than 385 GeV, which is a significant limit. And this has been known for many years. This is not new. But it's an example of how this kind of thing works. So I put this axe handle here to indicate an important constraint for new physics models. Now, Marina already described the CKM matrix here. I just show it to remind you of the different variables, and you can refer to it. I'm not going to discuss it. Now, it's often said that we have not seen new physics. Yet what we actually observe, especially in flavor, is the sum of standard model plus new physics. Because we observe processes, lots of processes. Okay. So if you're observing something, you don't really know which is the standard model part and which is the new physics part. So how do you set limits on the new physics? Okay. Well, you can make hypotheses, and then you can make other hypotheses. So one common thing to do is say that tree-level diagrams are dominated by standard model, and loop-level diagrams could contain new physics. So here's a tree-level diagram, which is basically a single W. And this is a semi-leptonic decay, where the W decays to a lepton and an antineutrino, and the B quark decays to a C quark or a U quark, and then there's a spectator antiquark here. So this is what we mean by a tree level. And here's what you mean by a loop level. This diagram describes B sub S mixing, where you have a B sub S bar that's a meson that contains the B quark, so this is a B sub S bar, and it transforms by this diagram into an anti-B sub S meson. Okay. And this is a standard model diagram. So the idea is that this diagram has two gauge bosons in it, so it's suppressed in some sense with respect to the tree level diagram. And you can have new particles here, for example, in some supersymmetric model. Then these two would interfere, and you could see the effects of this in this diagram. So that's the ansatz for this. Now, you can also look at lots of other processes. Now, what I'm going to show you is some diagrams in the rho eta plane. So let's go back and remember what rho and eta are. Rho and eta are these CKM elements, fundamental constants of nature that can't be predicted but can be measured. Okay. So in the rho eta plane, sorry, I'll get to the right place here. In the rho eta plane, you can make measurements of various things. Marina described the VUB measurements on Monday, and you get it, regardless of the theoretical and experimental uncertainties here, you get a band. And then there are measurements of this angle gamma, which is a function of the parameters rho and eta. And you get, from these measurements, you get a reasonable location of the eta and rho parameters. Okay. But these are all determined by tree level diagrams. Okay. You don't have any loop level diagrams appearing in here. Then you can do something else. Now, I could spend 2 hours describing all the measurements in here. I'm not going to do that. I'll describe this sine 2 beta measurement later on in the talk. So these are measurements all involving loops of one kind or another. One involves B sub S mixing, the diagram I showed you. There's another involving B sub D mixing. There's another involving CP violation in kaons. Okay. And the sine 2 beta measurement, which is CP violation in B0 decays. And you get another region here. And at first glance, this looks rather similar to the region we got with tree level diagrams. So we can overlay these, and they're in pretty good agreement. Let no one tell you they're not in good agreement. They are, but they're not in exact agreement. Okay, so the consistency, there's a consistency, but it's only at the 5% level. And you can from the difference here, you can derive limits on new physics, having made that onset. Now, having done all of this, and I'll show you some more details on it later, you could take a different approach and you can say, gee, we've looked at these things and we've compared tree and loop level diagrams, and boy, it seems to us that if there is new physics, okay, and we parameterize it by taking a Lagrangian, which is the standard model Lagrangian, and then writing this down as coefficients of order 1, and a scale order, an energy scale of order lambda squared times some operator here, then if we plot what the scale of lambda is from our measurements in CP violation kaon decays and B0 mixing and B sub S mixing in CP violation and even in charm, what you see is you get a range of values here, and these ranges are very, very high, okay? In fact, the strictest one is from K decays, and that's on the order of 10 to the 4th TeV, which is a little bit higher than 1 TeV, which is the scale the LHC is probing. So you begin to think that, gee, you know, either these coefficients have to be awfully small, which we wouldn't necessarily understand to get this down by 4 orders of magnitude, or this is telling us something actually rather profound. This is TeV. It's correct. If you don't believe me, you can believe these guys, because they've written it down and published it. TeV. TeV. Okay? So, but there are some ways out of this. You can say, well, the new particles really have large masses. They're much larger than 1 TeV. Maybe they are 1,000 TeV or so, and the coefficients are 0.1, or maybe they're 100 TeV, and the coefficients are 0.01. That's for depressing it. Now, there's another way out. And it turns out that since these are in loop diagrams, if you have two particles and they're of opposite phase and they come in the loop, they can cancel each other out. That would be some kind of a miracle, but it's possible. If the new particles have degenerate masses, truly degenerate masses, you can avoid this. Now, there's another way of avoiding it. You can say the mixing angles in the new sector, whatever the new sector is, are small, and they're same as the standard model. That's called minimal flavor violation. It's not really a theory. It just says that all these angles, the CKM matrix of the new physics is the same as the old physics. We don't know why that would be, but if it were true, then you would avoid this. Now, I don't know any other ways out. So what I'm telling you is these measurements already imply strong constraints on new physics, very strong constraints on new physics. But there are ways out. Oh, well, in here, there are various assumptions made, and it's just giving you the range of the assumptions. Okay. it can always be bigger than this. But this is not a bound on it. This is where, for any particular one of these calculations, you reject new physics if it's lower than this. So in one calculation, it's 10 to the 3. In the other calculation, it's a few 10 to the 5th. So it's a range of limits that you get depending on what you do and which process you actually use. Okay, I could have drawn one line, but I didn't know where to draw it. So
it's basically a range of limits.
It's a range of limits, right? It's a range of you can pick whichever one. It's a range of limits, right? In each case, but you can see they were all consistent in the sense that, okay, these decays haven't been studied as well as the others. Doesn't mean it's okay. Let me continue. Okay, neutral meson mixing. All right. So here's again a box diagram, but instead of just being for B sub S, I generalized it. Now, to be completely honest, you can also flip the W and the Q's in this diagram, but it doesn't add anything to this discussion. Okay. So we have a heavy quark Q, a spectator antiquark, and we have a CKM element here, and we have an exchange quark here, or exchange quarks, you sum over them, and W's here. So we go from a meson to an anti-meson state. Actually, go from an anti-meson to a meson state, but it's all right, it doesn't matter here. So neutral mesons can transform into their own antiparticles via second-order weak interactions, as shown here. The short-distance transition rate, that is how frequent this occurred, okay, depends on the mass of the intermediate state. The heavier this intermediate state, the larger the amplitude is. So this favors big Q being S or B, since you can have a T quark here, and a T quark is very heavy. So that gives you a large amplitude in general. Okay. Now the CKM elements in here are very important. Some are smaller than others, and some are larger than others. So when you put this all together and you take your heavy quark, for D0, since the intermediate quark here can only be, the heaviest one is a B quark, you don't get much. And the probability is almost 0. So you basically see a D0 decaying as a D0 most of the time, and very little D0 bar comes out. This is proper lifetime here. This, for a B0D, okay, on the other hand, you see an oscillation. It's not much of an oscillation, and this is the proper B0 lifetime. So you have to go above sort of at least a half a lifetime before you see much, and then it peaks at about 1.5 lifetimes. And the B0 to B0 rate is declining. Now for B sub S's, because the CKM elements are bigger, you get very rapid, very quick oscillations on very short lifetime scales compared to the lifetime of the, and these are accurate, okay, in terms of what you would see. Okay, now a little bit of mathematics. Okay, so here's the diagram. Now, when we talk about oscillations of D's or B0s or B sub S's, what we're talking about is writing down your Schrodinger equation, okay, that relates the initial states, the time dependence of the B sub S0 and the B bar sub S0, and this time dependence comes through a mass matrix M and a width matrix gamma. Now CPT ensures that M11 equals M22 and gamma 11 equals gamma 22, but then there are these off-diagonal matrix elements. So you diagonalize the matrix. And when you do this, you get a light eigenstate and a heavy eigenstate in terms of these parameters P and Q. Okay? So you get ML is P M0 plus Q M0 bar, and MH is the difference. Okay? And then you get the B sub, what you call the mass is just the sum of these divided by 2, okay? And you get a delta M, the mass difference here. Right? And the lifetime is just defined in this way, and you can have a difference in the lifetimes. Now, the phenomenology of the systems depend on the system. Okay? For example, Ks, which I'm not discussing, have very large delta gammas, which is just because of phase space, if you recall. Okay. And then this is a parameter Y, which is often used. It's just defined as delta gamma over 2 gamma. Okay. Now, you can consider differences now between m bar going to f and m going to f. Now, if f is a CP eigenstate, this is very simple, okay? And well, in the sense that it's easy to understand that either m bar can go to f or m can go to f. Because in the CP eigenstate, you can't tell whether it's actually, if you look at a CP eigenstate, you can't tell whether the particle that decayed into it was the particle or the antiparticle. For example, B0 to pi plus pi minus, you can't tell that was a B0 or B0 bar. And because it's a fixed angular momentum state, it's a CP eigenstate. So we define AF in terms of m to f, and AF bar is m bar to f. And now there's this quantity lambda, which is very important. Remember P over Q from the last transparency, and A bar F over AF. So lambda F is just a product of these two. Okay, so this means that this amplitude to go from m bar to f could be different from the amplitude to go to m for f. But there's also a P over Q, which is the difference in the mixing, okay, that we saw here. Okay, so here are the P and Q terms again. All right, now lambda f is a function purely of the CKM elements. That's an important, a very important thing. So whatever the CKM elements are, lambda f is a function of it. And don't forget, some of the CKM elements have imaginary parts. Anything, eta is the imaginary part in the CKM matrix, okay? So lambda f can well be imaginary, or have an imaginary part, actually. So now, to simplify things for the moment, I'll just consider the case where the magnitude of lambda f is 1. And then you can write the decay rate for m to f as a function of you know, the lifetime. This is e to the minus t over, it's gamma t, so that's t over the lifetime for whatever the state is. And then it depends on the width difference here, okay, and then in two terms, and it depends on the imaginary part of lambda f and a term that oscillates with the mass difference here, delta m. Now, if I don't assume lambda f equals 1, I pick up a few extra terms, and you have to put those in eventually, but you don't have to worry about it too much. Now, if you have m bar to f here, what happens is that this just switches terms. So for the case where lambda equals 1, you get a very simple expression for this asymmetry. It's just twice imaginary lambda f times the sine of delta mt. So let's talk about the B0 system. So what you can do here, let's take a CP eigenstate. Let's take J psi k short, the most famous one probably. So you can have B decaying through the amplitude lambda f to J psi k short. That's a B0. Or it could mix. Now if it mixes, you pick up this Q over P term here, and then it decays through A bar f into f. And they both these terms are here. So if I construct this asymmetry, this is m bar to f minus m to f. Okay. I pick up this term, 2 lambda f, 2 imaginary part of lambda f, and here I allow lambda f not to be equal to 1. So I have a 1 plus lambda f squared. This is very close to 1 generally, so this is back to the original imaginary lambda f sine delta mt term. And then there's another term which is only finite if lambda f magnitude of lambda f is not 1. And then you get a cosine delta mt term. And this is called direct CP violation, because it comes from CP violation in the differences in the A's. Okay. So if I now can take my diagram for B decay into J psi k0, okay, I can see what the CKM elements are here. So there's a CKM element here is VCB. The CKM element here is VCS. Okay, and if I write down what P over Q, A bar over F, A bar over A is, I get all these terms here. And the only one that contains an imaginary part is this one. And this one comes from the mixing diagram. So these come from the decay, and this one comes from the mixing. And the only one that's important in terms of the imaginary part is the mixing. Okay? And you have to multiply this by the CP of the final state, which is odd in this case. So you pick up a minus sign. So it turns out that this lambda f term is e to the minus 2y beta. Okay? And then you have to take the imaginary part of it and put it in here to get what the CPA symmetry is. And I just remarked that in terms of the CKM elements, tan beta is equal to eta over 1 minus rho. So you know what beta is. That defines beta. So putting it all together, ignoring the, taking the case for lambda f equal 1, you basically get that the asymmetry is sine 2 beta times sine delta m over t. And then you look for the cosine 2 beta dependence to see if lambda f is really 1. That's how you do it. So here's the experiment. This has been done by very well by Babar and Bell, and LHCb is also starting to get some data. So let's look at the Bell measurements. They've done both J psi k short and J psi k long. You can see the sine wave starts out negative here and comes positive. This is determined by delta m. It's only the height of the curve that determines the CP violation. And this is a state J psi k long, which can also be looked at, which has opposite CP. So you can see the curve comes up positive here. So you just measure the amplitude of the oscillation. And this is Babar data also, similar case. And the values come out to be fairly accurately measured. And this is the average. We had no knowledge of what this was going to be. And this is the direct CP term that's measured consistent with 0. Okay. So this is a precision measurement. You saw it already. I showed you it on the plot. So now you can go back and ask the same question again. Is there new physics in BB bar mixing? And what you do here is you write the amplitude for standard model plus new physics in BB bar mixing as the amplitude for the standard model times something new, and the new thing can have a real part and an imaginary part. Okay. And then you can do a full analysis using the sine 2 beta measurement and also other measurements, all other measurements that you can get your hands on. And this has been done by the CKM fitter group, for example. And here's the standard model point. Now, this is exactly the same as what I showed you before, with overlapping the two diagrams, just another way of doing it. So the standard model part has no imaginary part, and the real part is 1 here. And you can see if you put all the data together, okay, you're pretty close, okay, but you're not exactly on the standard model. So there's still room here for new physics to show up, despite what everybody else has told you. This is how accurately you've measured it. Okay. So there are different ways of looking at this. On the other hand, the 1000 TeV is also true. So it depends on what you're doing and how you want to look at it. All right, delta MS. So in B sub S mixing, remember the mixing frequency was rather large. Okay, so here's the evidence for it. This was first seen by CDF, and you can see a peak at 17.7. I don't have time to discuss this, but you can ask me. And here is the LHCb data where you can actually see the mixing oscillation term for B sub S. So for B sub D mixing, the delta M is about half of inverse picosecond. For B sub S, it's 17.7 inverse picoseconds. So that shows you how rapid the oscillations are. Now, having done that, one can look at CP violation in B sub S system. Okay. So what's been looked at is both J psi phi or J psi pi pi. Okay. So here, again, it's very similar to B0, but it's very new. And if you write down what lambda f is here, the prediction of the CP violation, you find that you predict that the phase of the CP violation in the standard model is negligibly small because there's no imaginary terms here or in the mixing diagram. Okay, the CKM matrix only to second order, which I only wrote down the first order terms for you. The second order, there's a little bit, but in here, there's, you know, the CKM terms are real, and in the mixing diagram, they're also real. So, because you have a VTS there instead of a VTD. Okay, so for that simple reason, you expect in the standard model to have negligibly small CP violation. So if you're an optimist, you say, well, that's great, because if I go back to the mixing diagram, I can have new particles in these loops, and they'll have a big influence. Whereas in B0, I didn't know what I was going to get. I'm sort of measuring a combination of rho and eta, okay, and I have no predictions for those. In B sub S, I could say, basically, I don't expect anything. All right. Now, this gets a little complicated if you look at the final state J psi phi, because J psi phi is not a CP eigenstate, because it's two vectors in the final state. And if you remember your undergraduate physics, that could be either CP even or CP odd, depending on the relative angular momentum between the J psi and the phi. Okay. It's either an SP or D wave. S and D give you the same CP, but P gives it. But a lot of clever people figured out how to separate out these components doing an angular analysis to separate the CP plus and the CP minus components. Okay. Now, for J psi pi pi, the situation is a little different. Okay. If you look at the pi pi mass, okay, you see a very large peak near 1 GeV, a little bit below, and that's called the F0 980. And that was first used to measure CP violation in this mode. But then this whole structure here in J psi pi pi was analyzed, and it was measured to be more than 97.7% CP odd. So at that level, you can use all of these events. You just say it's all CP odd. Okay. So doing that, you could just make a very simple CP violation measurement by measuring the, just as you did it in J psi k short. Just make the same measurement, except that you actually don't see anything. So you get a number consistent with 0, which is consistent with the standard model, with actually reasonably large error of 0.17 radians. So it's not, it's certainly small. Now, this is just to illustrate how difficult this is, but it's actually, people have done it. So the J psi phi final state breaks up into a sum over 10 amplitudes. And these amplitudes are defined in terms of angles, okay? Well, you have the product of these coefficients times these angular distributions, and the angular distributions depend upon the decay angle of the psi, the decay angle of the phi, the angle, and the angle between the two decay planes. Obviously, we're not going to go into this in any detail. Just to show you, if you were describing J psi phi alone, you'd have 6 decay amplitudes. But there's also the possibility that the K plus and K minus and the phi are actually not making a phi. There's a scalar state also, the F0, for example, below the phi. Okay. So you have to consider that scalar state too. So that adds another 4 terms in, which doesn't make it easier. And then the amplitudes themselves are written in terms of the decay in this way. Now, I'm not going through all of these. Just to show you that for J psi pi pi, you only have one of these terms. That's the full term. And so that's much simpler to deal with. But you can do it. So LHCb, a lot of experiments have done this. CDF, D0, LHCb twice now. And here are the contours of the results. Okay. So originally, D0 had a measurement that was consistent almost with -1 radian, and CDF also was fairly large. The errors were large, but now you can see the LHCb results very close to the standard model point. So this is a plot of delta gamma S versus phi S. So this is a CP violation, and this is the width difference. And you can see the width difference is now, you can establish a finite width difference. So you can see that there's a width difference, delta gamma, that's about 0.1 picosecond. And gamma is about 0.65 picosecond. So the width difference is actually rather substantial and interesting. And because you're measuring, the way you're measuring phi S, you actually have ambiguity here. But you can look at this interference with this S wave, which I said was a problem, and you can get rid of the ambiguities that way. So the combined result from LHCb is consistent with 0 with an error of about 0.08 radians. So it's consistent with the standard model. But one wants to do this measurement with a lot greater accuracy. And Atlas was also getting into the act. They also made a measurement here. But you can see the errors are much larger. But it's interesting they can do it. So this is a constraint. So no new physics models can produce large asymmetries. All right, if you look at delta gamma versus gamma, I think I'm going too long here. You can see that this is a world average of all the results, and you can compare it with the theory. So it's very well explained by the theory, and we have now very good numbers for delta gamma and the lifetime of the BS. So let me go on here. The semi-leptonic asymmetry, by definition, this is constructed differently because you have an F here and you explicitly have an F bar here. Okay. At t equals 0, m bar to F is explicitly 0, as is m to F bar. But because of mixing, you can pick up an asymmetry here. So what you can do is measure B sub S bar to D sub S mu nu versus B sub S to D sub S minus mu nu. Okay, this is a very good way to do it if you want to measure the semi-leptonic asymmetry in B sub S decays. Or you can actually look at dimuons. Okay, so you have two B decays, and you can look mu plus versus mu minus, where one is providing the tag and the other is doing the decay. So in the standard model, if you go back to slide 16, you can predict this, and it's essentially vanishing. Okay. Now D0, the interest in this picked up very much when D0 used this dimuons and made a measurement that correlated ASLS and ASLD, and this is their measure, and the angle here is governed by the measured fraction of B sub S and B sub D mesons compared with the standard model. And you can see there's a difference here. These are 1 sigma bands. So they had a 3.9 sigma difference. And they tried to separate this using muon impact parameters. It's not as accurate, but you get the idea that you know, you separate it and the value comes out around here. And most people, well, blame this on B sub S, even though the error when they separate it is very large. And then D0 did another measurement where they did the D sub S minus versus D sub S plus correlation. And here you're just looking at the final state like this, where the D sub S goes to phi pi, actually. The two kaons form a phi. And here's the D0 result. I have a little quibble with this in that they suppress the 0, so it makes it look like it's more signal to background than it really is. But you can see the D sub S and the D plus peaks merge together, but you can separate them doing a fit, and they have something like 203,000 D sub S plus events and about the same number of D sub S minus events. And they have a number which is sort of consistent with everything, their previous result and the standard model result. And they also make a measurement of ASLD separately with that value.
How do you define ASLD?
ASLD? How do I define it? Okay, I'm not sure what you're asking, but let me go back to here. This is the definition of ASL. So ASLS is when this is a B sub S, and ASLD is when it's a B0. Does that answer your question? Okay, good. Thank you for the question. It makes me feel better. Okay. So here's the world according to D0. So the world according to D0 is the standard model is here, and all their measurements are basically give you a value here. Okay. So they have a ASLD, which is, you know, a little higher than the standard model, and an ASLS, which is significantly negative at the level of 3 sigma. But there's a new kid on the block, and that's LHCb. Now, the LHCb just measures D sub S to mu nu, okay? And there's some experimental details here which you don't have to go into. This is a log scale. So this is D sub S plus versus D sub S minus for LHCb. You notice these peaks are completely separated now. There's lots of events in here. The effect of you might argue that there's a production asymmetry possible at LHCb. In fact, there probably is a production asymmetry, but it turns out that the rapid mixing oscillations coupled with the slowly varying acceptance reduce this to a negligible level. And LHCb uses a large number of calibration samples to measure the detector, trigger, track, and muon ID biases, which is essentially what takes up all the time. Getting the signals is easy. Getting the calibrations is hard. So what LHCb found was a value that was very consistent in the standard model with AHLS with 0 of minus 2.24, a quarter of a percent with an error of a little bigger than half of a percent. And then the B factories even have updated measurements now for ASLD, which is completely consistent with 0. So this is the world according to not D0. And it's all consistent with the standard model. Okay. And in fact, there's another, if you go back and work through the equations, you expect phi s to grow, 2 beta sub s is phi s. So for a finite ASL, what you measure here would grow to a larger value than we measure for phi s. In other words, seeing a large value of this means you'd see a large value of phi s in general. Now you can look at the CKM B sub s fit here, and this is the standard model point here, and you can see that it's completely consistent with the standard model, but their errors are reasonably large, so one can hope that if you push the measurements down, you can do better. Now let me turn to B sub s to mu mu. The standard model branching ratio here is pretty small, 3 parts in a billion. Okay. So this used to be a dream. Okay. Now there's a 10% correction that has to be made because of the finite delta gamma here. So this is really like 3.5 10 to the minus 9. So in the standard model, there's 2 diagrams which are fairly easy to compute. And for other new physics models, you get other diagrams that depend on the content of the new physics models. This is the MSSM, and it goes as 10 to the 6 beta, but this could be anything. Okay. Now, it's worth describing a little bit how this is done. Now, LHCb has a tremendous advantage in that B sub s to mu nu is pretty much like B to k pi, except that you identify the muons. So LHCb, cultivates these decay modes, pi pi, k pi. This is an important part of the physics program, but also it allows you to study exactly what the kinematic properties of these decays are. So before you apply the muon identification, which of course has some fake rates in it, you can learn how to isolate your B's and get high efficiency. So that's what's done, and all kinds of experimental quantities are used, like the impact parameter that's of the B, that is how well the B points back to the primary vertex, the B lifetime, the B transverse momentum, the B oscillation, the muon isolation, the minimum impact parameter of the muon tracks, how far they are from the primary vertex, et cetera, et cetera. So what LHCb does is they set up this discriminant. It's a multivariate discriminant. So you don't make individual cuts. You just use all the cuts in common. And the signal probability is tuned to be almost flat. And the background probability falls by 4 orders of magnitude. So you're really sensitive at high BDT values, although all the data is actually used. And you also, if you measure a branching ratio, you actually have to know how many B sub s's you have. And LHCb, Marina showed you this before, LHCb measures Fs over Fd, and that's the number of B sub s over number of B sub d, and that's about a quarter. I'm going to skip this because you already saw this. Now, new news on this is that this has some kind of transverse momentum dependence. So other experiments, such as Atlas or CMS, that use the LHCb value of about a quarter have to make sure they understand their PT dependence, because they're not measuring in the same PT range that LHCb is. Okay. So here's the LHCb evidence for B sub s to mu mu. This is from the first data sample, and this is the second data sample. And these bands, okay, the B sub s band is this red band here, and the green band is BD. They slightly overlap. But you can see that there are events appearing out here at high BDT, okay, in both cases. And if you make a cut at a BDT of 0.7 and plot it up, you see a small peak at the B sub s mass, And here are the projected backgrounds, which are at low mass and small. So there's a 3.5 sigma excess. This isn't proof that it exists, but it's evidence. And the branching ratio, unfortunately, is right on the standard model. I mean, it's not, at one point we were hoping for much larger because of this 10 to the 6 beta. At another point we were hoping for much smaller, and what we got was right on. And here, for example, is the history of this, previous limits from, you can see this is a log plot. So this went down rather quickly with time, and then this was LHCb, and this was the combination as of last summer, and now LHCb actually has a result at the standard model value. Okay. So there are a lot of implications of this because this puts very severe constraints on many models, including, you can see standard model-like, so anything with 10 beta above this standard model-like line versus the mass of the A boson, okay, is ruled out because we're already at the standard model level line. So you can make many plots like this in many different models. B sub D is also restricted. These 4 muon modes were looked for and not seen. If you look at the branching ratio of B sub D versus V sub S versus these models, you can see that this region has been ruled out. SM4 is a 4-quark model, but most of this phase space of these models is gone. This is phi S versus the branching ratio for B sub S to mu mu, and again, most of the phase space of these models is ruled out. The 125 GeV Higgs observation essentially kills off these 4th generation SM4 models with single Higgs doublets, as the production cross-section would be 9 times larger and the decays to gamma-gamma suppressed. So there's a different axe on this. Okay, let me, a little about charm mixing. Various experiments have seen evidence for charm D0, D0 bar mixing, but none with a significance greater than 5 sigma. This is easy to look at. You look at D star plus to pi plus D0, and then the D0, if it decays like a D0 bar, that's mixing. Or it could also be doubly Cabibbo suppressed decays, but doubly Cabibbo suppressed decays follow an exponential dependence, whereas mixing follows the sign pattern. So you can distinguish these. So you define R sub D as the doubly Cabibbo suppressed rate over the Cabibbo favored. And mixing is parameterized by X prime versus Y prime. So you can write down the decay rate as a function. This is what you don't want. It's doubly Cabibbo suppressed decay. The doubly Cabibbo suppressed decay also comes in here in a small way. And then this is the mixing term that you really want to see. And you don't see the sign term because it's too weak in oscillation. So it just goes like this. All right, so what's the result? This is the right sign from LHCb. Notice this is 1 million events per bin. So you can't do this, with a low statistics experiment. So this is, the cleanliness of this is quite remarkable. You don't see any background. Now in the wrong sign, you see background. But this is an enormous wrong sign signal. And if you look at the time dependence, you can see this linear time rise that was predicted from the previous formula. This is the ratio of wrong sign to right sign, clearly. And that's one of the other reasons the sign term disappears. So this is beautiful. And this shows mixing at like the 9 sigma level in terms of the X prime and Y prime parameters, which still need to be measured with more precision. But it looks like it's all in Y prime, which is the delta gamma part that's doing it. So again, this is sort of a constraint on new physics can't do too much to this. There's also been some talk about CP violation in charm. After this paper from Grossman, Kagan, and Nier, they said, look, in singly Cabibbo suppressed decays for CP asymmetry, same CP asymmetry definition as in ASL, but there's different physics. And LHCb, CDF, and Bell measured the CP asymmetry difference between these, and it's come up to a 4.5 sigma effect. One wonders whether it will stay. Both standard model and new physics explanations have been prolific, and I would just treat this as a limit on new physics, that the CP violation can't be too large in charm, in singly Cabibbo suppressed charm decays. There's a lot more. One of the most important ones is K star L plus L minus. This is an exclusive decay, unlike S gamma, but like K star gamma. And you have two standard model diagrams here, plus new particles and loops that can contribute. Now you can look at several variables. The mu1 forward-backward asymmetry is well predicted in the standard model. That is, if you go in the rest frame of the dimuon system, the angle of the mu plus with respect to the B direction is an angle, and this angle can have a symmetry to it. And that asymmetry can be a function of q squared. And new physics is very sensitive to that. So first, the data. This is the data from 4 different experiments plotted versus the theory. Well, this is just form factors. This is not really a way of looking for new physics, but could appear here. So this is just a cross-section. The branching ratio is a function of q squared. And you can see the LHCb data have by far the smaller error bars here. Now, if you look at the forward-backward asymmetry as a function of q squared from LHCb, it's depressing. This is the theory here. These regions are removed because you have j psi and psi prime decaying to mu mu. And what you see is that it agrees extremely well with the standard model. I'll discuss what these things mean later, but they're just manifestations of new physics models, and they clearly don't agree with the data. I'll skip that. Okay. You can also measure the zero in the forward-backward asymmetry where I should have said this before. Okay. So where this crosses 0, where the data cross 0, you see it comes down and the data cross 0. This is very sensitive. It can be predicted in the standard model. Whoops. So this is well predicted in the standard model, and LHCb finds this value, which is completely consistent. It essentially rules out light stop at less than 400 GeV in this model, in the CMSSM. Okay. By comparing, again, the data and the theory. I don't have time to go into detail. It's actually very important sets of measurements you can do. You can measure model-independent parameters. There's a nice paper by Das and Sinha, which is fairly recent, which shows how you do this and how you can really say whether this is standard model or you can see any evidence. And there are many other angular observables that can be investigated for new physics effects. Now, generically, remember those C9 things that appeared before? You can write down a generic Hamiltonian for rare decay processes like this, where you write it in terms of coefficients and operators. So for this, the Ci, Oi are standard model, and the C prime, Oi prime are new physics, and the operators are basically chirality reversed. This is one prescription for looking for standard model physics. Here are the operators, including scalar operators and pseudoscalar operators, etc. So this is just a form. This is a form for looking at new physics. It's just one way of doing it. Now, each process depends on a unique combination of operators. Okay. So this process, K star gamma, which I haven't talked about, where K star goes to K short pi 0, you can measure the CP violation in this like this. So you get the direct term, this is the cosine term, and then you get the indirect term, the sine term. Okay. In the standard model, you can predict this. And then this, in general, depends on these coefficients C7, and if there's new physics, C7 prime. So that's basically how you deal with this. And the measurements from Bambar and Bell are actually poor, but they're still useful even with a large error, and hopefully they will be improved. You can also do this similar thing for inclusive beta XS L plus L minus. That was done by the B factories. So you can see signals here over backgrounds. And again, my point here is that these are sensitive to other coefficients, namely C9 and C10, as is K star 0 L plus L minus, which you already discussed, which is sensitive to C7 at low q squared and C9 and C10 at high q squared. Okay. So you can put all of this together and do a common analysis. This hasn't been updated, but you get the, I wanted to show you that each process here contributes. So you can limit the new physics parameters, like the imaginary part of C7 versus the real part of C7 prime. This is C7 prime also. But you can see the allowed region from each process. You can get the overlap regions here. And they're consistent with the standard model. And here's C9 prime and the imaginary real part of C9 prime. And again, everything is really consistent with the standard model. But these things are, they're useful. They make pretty pictures. And you can sort of see whether there's any new physics in any particular area. Unfortunately, none has shown up yet. The standard model is 0, 0. You don't expect, these are all new physics parameters. Okay? This is a new, as I defined it, the primes are all new physics parameters. Now there are plots that these guys make of the old physics parameters too, and the correlations between the new physics and the old physics. So there are lots of things you can do with this, and it's a very nice prescription, but it hasn't shown up anything yet. Okay, now beta tau nu. Now beta tau nu is a tree process, so it shouldn't show new physics according to our previous prescription. But to show you how things can be interesting, okay, let's consider this process. Now, prior to this summer, if you looked at sine 2 beta from J psi k short, which I showed you the measurement, versus the measurements of beta tau nu. So here's sine 2 beta, here's the branching ratio of beta tau nu. This is the measurement here. And this is the fit to the CKM to all the parameters I showed you in those two plots earlier without these two measurements. So this is a prediction, if you will, from all other measurements. And you can see this agreement here stinks. It's really bad. So people, there was a lot of papers written about this. In fact, this was one of the strong inputs to the fact that the fourth generation model may have something to say. In fact, Amarjit Soni wrote a paper which said the demise of a standard model. That was the title. Okay. And it turns out, well, and this could be a big problem. This was a big problem. Okay. Now what happened was Bell made a new measurement. So the Bell measurement now is the demise of that paper. Now, this situation isn't completely cleared up because there are 4 measurements, 2 by Bell, 2 by Babar. Babar hasn't revised anything. Bell has only revised one of them. So the average is still, the average is maybe here. But I think the direction is clear. Okay. So we need to wait for the Babar measurement to be sure of that. But now you get, well, it's actually interesting, but this was Bell's old result here. You can see this is difficult. This measurement is difficult. The signal is this little piece here. Okay, one should be aware of when things are hard. So this is the extra. When you do this, you want to reconstruct a fully reconstructed B meson, and then you want to look for something that looks like a tau, which is either a muon or electron or a rho with nothing else there. So you look for that. Suppose you find a muon. Then you say, how much extra energy is there in the calorimeter? And you plot it. So you should have no extra energy. So the signal peaks near 0 here, okay? Or at least it should peak near 0 here. And you can see their old measurement. Well, this is the size of the effect, okay? Now their new measurement, they're a little clever. You can see the peak is much reduced, but what they do is you can also take the fully reconstructed B that gives you a B direction, and then the particle from the tau, and construct the missing mass squared off of that. So it gives you another variable. So when they do that, and then they can do a 2-dimensional fit. And the signal Monte Carlo looks like this, and the background looks like this. So you could use the background to constrain the background here, is what it turns out to, and that's why they got a smaller signal. Besides which, they improved their tracking. So there were a lot of changes here, but the analysis was new. Now, having said that, there's another tree-level diagram. This is a semi-leptonic decay. It's exactly the same as beta D or D star E nu, except you have a tau. Okay, and it's much harder to reconstruct this because you're missing 2 neutrinos. You're missing a neutrino from the tau decay, at least one, and a neutrino from the from the B decay. So Babar did an analysis where they fully reconstructed 1B. They kept the events with initial D star plus an E or a mu. So they're missing 3 neutrinos. So then they construct the missing mass square, just as I described before. They take what they see from both B's. What? I thought you had a question. Is that a question? No, it's 10 minutes. 5 minutes will be fine. Okay. So they fully reconstruct 1B, and then they compute the missing mass squared with whatever, off of the D star and the electron. And what you see here is, here's where there's nothing missing. And it's really a D star mu nu, let's say. And then the black is where they have a D double star, where they're missing something, but pion from the D double star decay, because D double star decays to pi D star, let's say. And then here's what they expect if they have a tau. Now, of course, and then, okay, this is another way of plotting it, but let's just look at this one. Now, of course, if this black stuff moved up here, in other words, the signal is not this. The signal is the green over the black, okay? And you have to believe the simulation. You have to believe you know exactly what's going on with these D double stars. So the signal is wide. There's a lot of background. And you have to be very careful with this. It takes a lot of courage. Nevertheless, they claim to have found in both the D and D star channels an excess with respect to the standard model of 2 and 2.7 sigma. And the sum is 3.4 sigma. But it's also inconsistent. If you plot what you expect in a 2 Higgs doublet model, you don't get consistent answers. I don't want to go into the detail here, but that's the effect of what they're doing. So they have this result out there. It's inconsistent with the standard model. It's a tree-level decay. And then if you say, well, what did Bell do? Well, Bell has some extremely early results, early results, and they have much larger values than Babar. Okay. This is what Babar has for D star and D. The Bell values are higher. They're in different modes, but the error bars are much larger. So I think the conclusion here is that Bell has to do this analysis, and we'll see what they get. We'll see if there's any discrepancy in that. Okay. Now, let me just hit a little bit on this, okay? A few more points. Could it be there are 3 classes of matter? I'm talking about the dark sector here. Standard model particles with normal SU3 cross SU2 cross U1 charges, dark matter particle with other dark charges, some matter having both, which is called mediators. I mean, the idea here is that the dark matter may very well have its own sector. It may not communicate with the standard model. Then you'd have to have these mediators between them. So people are searching for dark photons. Okay, so mediator, it's an oxymoron, but it's cute. A mediator coupled with B quarks, for example, and you can do this search. So 1s going to invisible and anything. And there's a host of other experiments that have looked at these dark photons, and you parameterize this between the efficiency of the mediator between the standard model and the dark sector and the dark photon mass. And you notice these epsilons are extremely small already. And these are regions ruled out by other experiments, and this is what you'd need to see G minus 2. And there are a lot of experiments going on that will limit this phase space region even more. Okay, I don't want to talk about that. Majoranas, I want to talk about this. There are several ways of looking for the presence of heavy Majorana neutrinos and heavy quark decays. Okay, and you know what they are already. Okay, so if they're their own antiparticles, they can couple to ordinary neutrinos. So the modes, there's modes analogous to neutrinoless nuclear beta decay, some of the modes, for example. So here's a diagram for neutrinoless double beta decay, and here's a diagram for a B quark to a C quark, okay? And it's second order weak, of course. And here's your Majorana, and you produce 2 mu minuses. So the final state would be D plus mu minus, or D star plus mu minus. Now, the L's here could be they could be E's, mu's, or tau's. They don't even, it could even be E mu, final state. Okay. So here are upper limits. People have looked for these. Okay. The EE mode is clearly not competitive with double beta decay. Now, the others, we don't know what to expect. If there are Majoranas, there's no calculation of form factors or anything. But these are unique measurements. I mean, nobody's ever looked at this before. So if you had a virtual heavy Majorana neutrino, it might show up in these kind of things. If it doesn't show up, it's too bad. There's another thing you can do is look for on-shell Majorana neutrinos. For example, in this process here, let's skip this one. You have B to U process, you have a W, it goes to a mu and a Majorana, and then the Majorana, or you mix with this heavy Majorana here, and you get a mu minus and a W, and the W goes to like a pi or a D sub S. So you get two mu on, you get a B minus going to a mu minus pi plus, which would be rather unique. This was looked for by LHCb and not seen. There were several other modes looked at and not seen. These upper limits are a few 10 to the minus 9. So they're really pretty tight, but they could be better. And you can translate this to the coupling to the fourth generation heavy neutrino, and these are by far the best limits available for that, as a function of Majorana mass, by the way. Okay, so let me go to my conclusions. Although there's no compelling evidence yet for new physics, flavor physics is very sensitive to potential effects at high mass scales. Okay. Another way of saying this is we may be better at not finding anything than Atlas and CMS. All new physics theories must satisfy these stringent experimental constraints. Now, LHCb has been particularly effective at dispelling effects with marginal statistical significance, although a few remain. Will some be found when precision measurement improves? Improving measurements such as B sub S to mu mu, B to K mu mu, CP violation, phi S, for example, may show new physics effects that need to be aggressively pursued. And we're looking forward to defining the next theory beyond the standard model, and there are new future facilities, Super Bell, and the proposed LHCb upgrade. Whoops, let me go back. Okay.
Thank you very much. Any short questions? We are already beginning that. Any longer discussion can be postponed to the tea time.
My question is about the DC meson. I think it can be produced at LHCb. Now it's not clear whether DC decays primarily through B decaying first or C decaying first. Is that likely to be resolved at LHCb?
Yes.
And at what level?
We've actually measured several new decay modes of the B sub C already, and that's being actively pursued. Now, the ones we've seen are the easy ones so far. Where the B quark decay. The ones we've seen are the easy ones where the B quark decays. So we've seen that.
So it's mostly seen with B decaying first?
Those are the ones we've seen, yes.
Okay.
But there's also a decay mode which has been brought up, interestingly enough, where the BC decays into a pion and a B sub S.
Yeah.
So we'd like to see that, but we haven't seen. We just started looking for it.
And with maximal B sub S oscillation, you can see same sign dileptons and things like that, can you?
Well, actually, we look for fully reconstructed decays. We look for the BS going to something like J psi phi or D sub S pi.
I see. I see.
We're getting good at B sub S's. So yes, there are people looking at that. I don't know if anybody's looking at a particular mode where the C quark decays yet first. Well, that would be a B sub S, yeah. Yeah, we started that actually about a week ago. Just because somebody was annoying us with it.
Any other question or comment? Yeah.
Dr. Chow, is there any prospect for these the B to DS tau new modes or the B to D tau new modes with LHCb?
It's being worked on. So there's a prospect. So I would not personally guarantee that it will be successful. It's very hard.
The three-pronged tau, is that the idea, or you can't say?
LHCb has some wonderful things that can, in principle, be used to distinguish background from signal. For example, you can measure the decay length of the B, and for certain decays that live long enough, you get a really good direction. So you get the direction of the B, and then if there's a D that goes out, you get the direction of the D. Okay. Then if you have a 3-pound tau, and there have been certain studies that show that there may be regions of phase space that we can get on where we could actually measure this. But it's a lot of work. It's not obvious. And LHCb, I'm proud to say, has a reputation of being scrupulous about the results. So.
Okay, one for the brain.
Trying to be scrupulous about the results is actually a more correct expression. So, I mean, people will look it over very thoroughly. So we'll see. We'll see if it works, but there are people working on it.
Thank you. And again, and
sorry, just have a quick announcement. So there are T-shirts available, IMSC at 50 outside right now, and it'll cost 175 rupees. So if you have exact change, that'll be appreciated. If you don't have change, if you can combine orders, that'll help us. So we'll see. Hopefully, we can try to do something about that. Yeah. The other announcement is that talks might be available online, so you can check that out. And last announcement, maybe we'll come back 5 minutes late after tea. 12. Yeah, 12:05. Yeah.